We've danced around the issue right this afternoon that Per eloquently started regarding what defines thermal comfort. That question still hasn't been answered, so we're going to grapple that now in this 20 minutes. And also, Per made it very clear that, in fact, ventilative cooling, there is a very big issue that you need to consider when you're looking at benefits of ventilative cooling. And that is, what's the cost of getting that air into a building? So Per said, look, worry about the energy cost of using fans to drive the air into a building, such as the HVAC system we've just heard, but HVAC systems in general. This is some data that was put together by Koen Steamer and Nick Bakers. And it demonstrates that if you have a traditional air-conditioned building and compare that on a like-for-like basis with one that's naturally ventilated, there's an order of factor 2 difference in the energy consumption. And the lion's share of that difference is in the fans and pumps to drive the air in and distribute it. Now, I know we're going to talk about, what are the thermal benefits, and that's actually the topic of this of today. But how we get the air in is critically important. That if you're going to use mechanical ventilation, we need to do a much better job than this, all right, to make sure that we are sort of advocating ventilative cooling. So natural ventilation, clearly, that green bar goes away, and we can talk about the benefits of getting more air and the comfort benefits. But if we're going to use fans to drive the air, especially in summer, whether it be at night when you're driving air through a system to go and cool the building, there are plenty of buildings that do that and using thermal mass within those. But if you're going to use fans to do that, you need to be very, very careful about then assessing the benefits of saving some cooling the following day when you've been running an HVAC system for 10 hours. And I'm not suggesting, it's not the previous talk. These are buildings in general that where you've got big air handling plants on roofs that are thermally massive structures, and you're looking at blowing air through to go and save the AC load the following day. People do this all the time. But you've got to make sure that you look at the energy cost of running big air handling plants on the tops of roofs for 10 hours to go and get those thermal benefits. Now, we're going to look at a building that I didn't design and I just reviewed when I was at the University of Cambridge, and it's the Houghton Hall building. It's a naturally ventilated building, and it's a good example of, frankly, how robust buildings can be when they've got exposed thermal mass, and hence the discussion earlier about what constitutes thermal comfort. This building, let me just walk you through it. It's got 5 stacks on the roof. It's just got opening windows. It's open plan. And what we see here is just the ground floor. And the idea for the ventilation solution for this is that we've got a challenge, which is to do with the sun's pathway round here. So we heard earlier about getting the facade correct in terms of making sure that we've got solar shading, because there's no point in trying to cure everything with natural ventilation, getting the facade right. And this building does indeed have brise-soleil around certain perimeters to minimise the ingress of solar gain on the hottest summer days, but then it uses natural ventilation to provide thermal comfort. Now, floor plan of the building, and this is the section of the building. And I'm not going to dwell on this, but the architect at the time was being supported by an engineer as to how air would move in this building during the summer day, during the summer night, and indeed in winter. We see this all the time, don't we? Squiggly arrows. The air is not intelligent, all right? The air won't go where it's told on a drawing, so you need to worry about where the air goes in a building. And headline is this. We've got a building that's naturally ventilated. There aren't any fans driving the ventilation. And this was the picture that was drawn by the architect. And the concept was this. On a warm summer day, and I'm using my language carefully, warm summer day, it's acceptable to have the interior warmer still, so the air in the space is inside is warmer than outside. So the idea of, on a still day, using buoyancy to drive the ventilation, where air comes in at low level and is rejected at high level, seems laudable, in my opinion, and I think it's right. However, if you look closely at this building is robust, and this is where sort of the aspects of what constitutes thermal comfort become important. This building has a lot of exposed concrete, a lot of exposed thermal mass. It was cast in situ, beautiful coffered ceilings in the office areas. And this is just open plan into the central atrium, which is heavily glazed. Now, the glazed area, I'm going to tell you, you'll see the data in a minute, it gets a bit warm. But actually, the office areas are nice and cool. So I'm now going to ask you, nirvana. Okay, we heard 2003 was a rubbish year in terms of it being a heat wave in 2006 earlier. So 2003, we monitored this building, and it does get fairly warm in 2003 outside. In fact, if you remember, it was the hottest year on record, and it got to nigh on 40 degrees in the outer perimeter of London. If I were to ask you, is 40 degrees centigrade an acceptable temperature inside the building if it's 40 degrees C outside? Show a hand if you think that's okay. Okay, show a hand if you want it cooler. Now ask yourself this question. If it's cooler inside than it is outside, which way does the air go in the building if you've got vents open at the top and vents open at the bottom? Does it do this? Just got to make sure that we get the answer to that very basic question right, because if you can't get the direction right, I'm going to assert you can't get the rate right. So that's important. So this building did this, and this is looking at some temperature data collected by myself and some others at the BP Institute, University of Cambridge, in summer 2003. And what you see is that this line here is the external temperature. These are the temperatures within the main floor plates. These are the temperatures that matter, because this is the air temperature in the occupied zone. And when it is, high 30s, you're down at the 30 degrees C level. You might not think that's nice. I'm not going to tell you it is. But 30 degrees C air temperature compared with an outside temperature of nigh on 40 degrees C is an improvement. Okay? And I think you'll agree with that. So actually, thermal mass, this building had no mechanical ventilation, no mechanical cooling. This building was night cooled. And it's just by night cooling this building and then having the thermal mass help absorb some of the heat. Now, from a heat balance point of view, what's happening is in order to get the temperature outside hotter than the temperature inside, and you've got heat being generated inside, what has to be happening is that the amount of heat being absorbed by the thermal mass, the rate at which heat is being absorbed has got to be greater than the rate at which heat is generated inside. And this is where the heat balance matters. So we have a thermally massive building, and it is a cooled building, where we are actually going to have a system, magic, thermal mass, that absorbs more heat than is generated inside the space. When you go and find actually how this building is being controlled and ventilated, you're going to laugh, but that's what we're going to do. This is what the temperatures were over the course of July and August. So it wasn't just one day. These are the temperatures in the space. This is the external temperature. And the second floor is a bit warmer than the other floors, but it's being capped at 30 degrees when it's getting up to 40. And invariably, it's in the mid-20s. This is July. This is the hottest day on record, 7th of August, 6th of August, around the 40 degrees C mark. Very good. And then it's plain sailing thereafter into September. And the question that we asked ourselves, well, this building did pretty well. We got 10 degrees C, not 10 degrees C of cooling versus the outside with this exposed thermal mass. And we asked people, this was a lovely lady called Schwatter, she was a PhD student at the University of Cambridge Architecture Department. She conducted surveys at different seasons of the occupants in this building. And she found that it's the summer that really I'm worried about. And in the summer, thermal comfort, remember it's 30 degrees C in the space, air temperature. Why isn't that at 7? Completely unsatisfactory. I'm not telling you it's lovely, but it's not outrageously bad as far as the occupants are concerned. So something's working. Something's working because there's something else going on in this building. There are two other things, or a number of other things, but things that we can control in this building that constitute thermal comfort. And thermal comfort is not just about the air temperature. Thermal comfort, and we heard about it briefly in the previous presentation, which is perceived temperature, resultant temperature. Actually, what constitutes thermal comfort is a few things. It's the temperature of the air, clearly. It's the temperature of the surfaces to which you are exposed. The flippant remark I will make is that no one's ever overheated in a cave. In a mine, yes, but not in a cave. And why is that? It's not just because the air temperature is cool, it's because you are in contact with cold rock. So the surfaces, the colder you can get those surfaces, then that will contribute to your thermal comfort levels. And there are some other things. Air movement, we heard about that earlier. And then relative humidity as well. That's more difficult to control in a naturally ventilated environment. So part of the reason why this is actually not as bad as it could be is that this building has lots of air movement as well. So it's air movement and surface temperatures as well as air temperature. So can we improve upon this performance of this building? Because this was a building that was designed well by the architect, and as a result of having the exposed thermal mass, we find that it's very resilient and very robust, even though in this particular case it wasn't particularly well controlled. And what do I mean by that? Well, look at this. This is some data that I collected, which is tracking the temperature maximum inside versus the temperature maximum outside. And in a thermally massive building, one would expect the temperature maxima and minima in a building to lag behind the temperature outside. That's what you would expect. And what bizarrely we find here is that generally all the data does show a positive lag. So yes, the building gets to its maximum temperature, sometime after the outside temperature's got to its maximum. So at 2 o'clock in the afternoon, it's really hot outside and it starts to cool as the sun's going down. The building's still heating up and it reaches its maximum temperature at 5 in the afternoon. The inverse happens in the morning sometimes, which is where the building actually got to its minimum temperature before outside. And the reason why this happened is that there was no clever ventilation system controlling the windows. But what happened is that the building management system detected that the building temperature was getting close to 20 degrees C. So in this building, on the 6th of August, the hottest day on record, the heating system kicked on. All right? So just be careful when you're looking at nighttime cooling that if you don't want to overcool the building, that you actually have some ventilating dampers or windows that close automatically, or be happy and set the temperature for the summertime temperatures to be at 17 degrees C rather than having the heating system come on. So we could have improved on that thermal performance by not turning the heating system on in the morning of the hottest year on record. Okay? So just sort of lessons learned. And this is the temperature. Generally, we got most of the time. It was between 1 and 4 hours that actually this building achieved this. So it's a thermally massive building. And what you can find is if you then go and run a model to find out how should you ventilate a building. So Per asked a very pertinent question just now. If you've got an interior environment that's cooler than outside, you've got a wonderful system, the thermal mass is absorbing more heat than's being generated, what should your flow rate be to maximise the use of the thermal mass in the space? You're in nirvana where you've got this free cooling system with thermal mass. I'll ask another question. If you go to Southern Europe on holiday and it's roastingly hot outside and you've been blessed with a farmhouse with thick walls, what do you do ventilation-wise on a hot summer afternoon? You close the shutters and you have minimum ventilation because actually that way you preserve a cool environment. What's actually happening is that you're maximising the effectiveness of the thermal mass to which you were exposed, all right, by not blasting it with hot air. Okay, you know this in your heart, that's what we should do with this building. What did they do in reality? This is what they did. So on the 6th of August, I walked around this building, and in this building, which had been night cooled, they had every window open. They were blasting it with as much hot air, 40 degrees C air as humanly possible, and they still achieved a 30 degrees C interior. Imagine what they could have done if they'd actually had a semi-intelligent, even intelligent ventilation system that actually did what you know is the answer already on how to go and achieve and use ventilation, free ventilation in buildings. And these were the air quality rates. So we just heard about it earlier in terms of, what are the ventilation rates? Look, they're getting, by measuring CO2 in the space, you're getting something equivalent to 60 litres per second per person, when in fact they should be doing this in this building in the height of summer to maximise and use ventilation in a clever way because you've got exposed thermal mass. In this particular building, they ran into some problems during the construction phase. I think the contractor went bust, and therefore it was all a bit awkward. It's a successful building, but as a result of that, some of the quality of the opening windows, which they used for night cooling, the window stays, weren't as good as they could have been. So in fact, they got less night cooling than they would have done if they just had decent quality windows. So that's another thing that didn't work so well in this building, and they still achieved great results. So, the opportunity is significant, but I'm not going to suggest to you that this opportunity is significant in the heart of London. And the reason is this. If you go and look at the nighttime temperatures in 2003, just outside the M25, every night it cooled below 20 degrees C. Nearly every night it cooled below 15 degrees C. And we heard earlier about the heat island effect. This building relies on the fact it cools down at night. And whether it's concrete or whether it's exposed thermal mass, and Zolt mentioned it earlier. We've got, there are products on the market which have got phase change material embedded ceiling tiles, phase change material embedded plasterboard. There are, exposed thermal mass is incredibly important, but it will only work if you can cool it down at night. And you need these temperatures. And the heat island in London is something I'm a bit nervous about in using, just free cooling. But most buildings aren't in the middle of London. We've only got 8 million people there. We've got 60 million in the country. So most buildings actually don't have this particular problem. So let me just give you one more example, which is the Contact Theatre, another building I didn't design. It just went and reviewed as part of a research project, again, at the BP Institute. And the Contact Theatre in Manchester. This is a naturally ventilated building with some stacks for ventilation and these vents here, which were designed for inflow. And this building is just another example. There is no mechanical cooling, but it's got a lot of thermal mass in the space. And here we are. This is the black line is the external temperature. This purple line is the target temperature is the internal temperature. And the target is basically 21. I assert that Alan Short, the designer of this theatre, has done a remarkable job. All right, it's fantastic. It's getting up to 25 degrees C, matinees here, and this is the temperature inside the space. And clearly when it's colder outside, he's still achieving these temperatures in the space. So there is no mechanical cooling, but it's got natural ventilation with thermal mass, exposed thermal mass in parts, but this one is mainly a plenum that they're using to go and pre-cool the air in this particular case. Now, Belvoir High School is one of our projects, and this is a school which uses natural ventilation. And on the face of it, it actually doesn't have much thermal mass. But by night cooling it, when you go and run dynamic thermal modelling simulations of spaces, you never account for the furniture because you don't know what's going in there. Our experience is that we find that when we design to meet summertime temperatures of, for example, if it has been a school, we've been designing to these standards where you meet 2 of these 3. Our experience is that by night cooling properly, the exposed mass, even in what is at first glance a thermally lightweight building, by good night cooling and then good ventilation, you achieve remarkable summertime temperatures. So we never got above 28 degrees C. This is the data in buckets. So it's just a natural ventilation system, and it could have been just a damper with a little controller in, and it could have been BreathingBuildings, it could have been somebody else, but natural ventilation with night cooling is a fantastic way of achieving what we've talked about, ventilative cooling, where we're not paying for the night cooling, there are no fans running to drive the night cooling, and we're certainly not paying for the ventilation during the day. And then where CIBSE has gone, and Ben mentioned this earlier, in terms of, what is thermal comfort? So the way that we are now assessing what we mean by a comfortable environment in buildings, it was started with CIBSE TM52 that was launched in the last 12 months, and then the schools programme in the United Kingdom, facilities output specification that was launched in October of last year, and it's about to be applied to all schools, uses this whole definition of perceived temperature. And the 2 really, really big factors are clearly air temperature, but also the temperature of surfaces to which you're exposed. So if you want to build a structurally lightweight building, because it's cheap for the contractor to do so, but you want it to be comfortable, you can create a thermally heavyweight building by using these phase change material embedded ceiling tiles in the ceilings, or phase change material boards. There are lots of materials, and by cooling surfaces down, you benefit not only in terms of cooling the air, but you as a hot body at 37 degrees centigrade, if you radiate heat to these cooler surfaces, you will derive that sense of thermal comfort, and that's how you will be assessed now. We talked earlier about, well, what are the regulations? Actually, you need to design buildings that meet the new summertime overheating criteria, which you can take great credit with if you've got exposed thermal mass. And if it's concrete, that's great, but if it's other forms of thermal mass, you'll also get the credit. So lastly, sometimes you might look at hybrid designs, and in my experience, the hybrid designs, for example, supermarkets, once you've done a great job at summer by using ventilative cooling and exposed thermal mass, The remaining challenge can sometimes be the very depth of winter and how you deliver heat to the space. So supermarkets are a good example where, because they don't want to put an underfloor heating system in or radiators, just because that's not what they do, when they heat a building, they want to duct air in, just for practical reasons. In that case, they end up with the answer being, if you're going to do ventilative cooling, free cooling, in other words, natural ventilation, not fan-driven air in the summer, they end up with more of a hybrid system. So there are examples where hybrids are appropriate. So in summary, I would sort of extol the virtues of ventilative cooling, but I would sort of put a flag up as to, let's think, and this is what Per said right at the very beginning, think carefully about how the air is being brought in, and if it's got a mechanical system driving that air in, look very carefully at the energy use that you are using, the energy use for driving that air in. If it's natural ventilation, clearly it's a very easy game. Exposed thermal mass, incredibly important. So if you've got some thermal mass, some thermal storage capacity in a building, exposing it allows you to reap much more benefit in terms of what now is widely known in terms of thermal comfort, because you are a hot body. And if you're not at 37 degrees C, you're very ill or dead. Okay, so you are a hot body, you will radiate heat to those surfaces. And then, say, fan-driven ventilation, be careful about the use of the term free cooling. Natural ventilation, I'll buy it. If it's mechanical, I probably won't. Any questions? Thanks.